Swayam Prabha. Digital India. Educated India.
Welcome back to another lecture on control systems. In the previous lecture, let me just quickly recap what we did. We actually saw this notion of asymptotic stability and compared it with the notion of Bibo stability, the erstwhile Bibo stability we had learnt during our foray into transfer functions, right. When we are dealing with classical control based techniques, we were already aware of something called Bibo stable, bounded input, bounded output stability, right. And we saw that this notion of asymptotic stability is a wider or a broader concept that already incorporates within itself the notion of Bibo stability. So then hereafter it makes sense to just talk about asymptotic stability, right, because that will automatically imply that it's Bibo stable, at least insofar as we are dealing with linear time invariant systems. The asymptotic stability seems to be the most powerful notion of stability as a matter of fact, right. Okay, so with that in mind, we actually saw this figure that we drew in the last lecture, where we saw that, well, given an ODE, given a system represented as a constant coefficient linear ordinary differential equation, yeah, you can go via this transfer function route and you'll only get as far as checking the Bibo stability. So that's why it's the external description, right, the notion of external stability. On the other hand, if you start from this ODE and go via this state space realization route, go to this state space realization, pick out the A matrix, find out the eigenvalues of this A matrix and check whether they are all on the left half plane, and you assure yourself whether it's asymptotically stable or not. And you find that if you can make it asymptotically stable, or if it is asymptotically stable, then it's guaranteed to be Bibo stable, yeah. So therefore this is an internal description of stability, right, internally stable, yeah. Now note that if your system fails to be asymptotically stable, you cannot comment about whether it's going to be Bibo stable or not, yeah, just by looking at the eigenvalues of A. So failure to be asymptotically stable does not mean it's also failure to be Bibo stable, but if you manage to be asymptotically stable, then you are guaranteed to be Bibo stable, yeah. So that is a point that you would do well to remember, and it's nothing big I am saying here. What I am saying is, if you just understand why they are not exactly both way equivalent, the reason is because of this possibility of pole zero cancellation. So if you fail to be asymptotically stable, it means that one of the eigenvalues of A might be on the left, on the right half plane, or on the imaginary axis, but it might so happen that this fellow gets cancelled by some zero, which is again dependent on the C and B matrix structures, right. And therefore when you look at the transfer function, these poles that are, or these eigenvalues that are on the right half plane do not make their appearance in the poles of the transfer function, right, because they get cancelled. So therefore you might still detect this system or infer that the system is Bibo stable, right. So what I am saying is that essentially when you are thinking of Bibo stability, you are just concerned with this Yt, yeah. What is this Yt after all? This Yt in our case is just a scalar, yeah, right, because we are dealing with seesaw systems, remember, single input, single output. On the other hand, the asymptotic stability is telling me that this entire vector, this vector's 2 norm, yeah, better be bounded, which means, here's the interesting bit, which means that each of them individually have to be bounded, yeah. So this must go to 0. If this goes to 0, yeah, if this goes to 0 as t tends to infinity, then this fellow must go to 0, this x1, this x2 must go to 0, this so on till xn must go to 0. If any one of those fellows fails to go to 0 as t tends to infinity, you cannot have asymptotic stability. So clearly asymptotic stability requires a lot more out of you, while the notion of Bibo stability just requires the outputs, which of course are functions of states. The output is just a function of state, it's a single output here, it's just c times x. So it's some particular combination of the x's. So you might actually omit that particular x which blows up, and then you will not see, like if you have decoupled the responses, diagonalized, very obvious to see now. If you have decoupled the system, and then you clearly identify that, say x1, x2, x3 till x5 they are all bounded, then x6, x7, x8 they are all unbounded, and x9 and x10 are again bounded. And suppose you choose your C matrix to be such that the entries of the C, the first 5 entries of the C are non-zero, the C matrix, then the next 3 entries are 0, and the last 2 entries are again non-zero, right? Then you are basically taking a combination of only the stable modes of the system, and those are being reflected as your outputs, right? So therefore, I mean, there is no way you are going to be able to detect, even if those modes x6, x7 and x8 are going unbounded, just by looking at the output. So this basically gives you an external description, right? You don't have access to everything that's internal to the system. You are not accessing all the states. All the states are not reflected at your output. This brings us to the notion of so-called observability. That means you are not able to observe all those states at the output because you put a 0 next to all these 3. Of course, this is a very special realization I am talking about and requires a lot of mathematical sophistication, but loosely speaking, if you are following the thread of reasoning that I am adopting here, I hope that you at least are able to appreciate why, for one, number one, this Bibo stability and asymptotic stability are different. Asymptotic would imply Bibo, but Bibo will not imply asymptotic. Similarly, failure to be asymptotically stable does not imply that the system will fail to be Bibo stable, right? So these are important notions, and now we have spoken long enough about these notions of stability and all that. So I will wind up this notion of this discussion on stability with the last bit, which I find not there in many of the undergrad textbooks, but I feel that this is something that's very interesting and that one should always look for, when you are sort of trying to reduce block diagrams. So we have seen earlier that when you are given this G1 and G2, that's equivalent to G1, G2, or rather G2, G1 in fact, if you are a stickler, right? Similarly, when you have this G1 and G2 in a parallel path like this, so then this is just same as G1 plus G2. So then this is the same as having this block like this, G1, G2, and this as your input output, right? Similarly, when we had this G sitting here and let us say this G2 sitting in the feedback like this, then we saw that, well, of course, this is a negative feedback that we are assuming. So then this is tantamount to saying that's G1 by 1 plus G1 G2, the whole thing. So we have seen these block diagram reductions, but these are all in the transfer function domain. Now we have now come up a long way from the transfer function domain, and now we are claiming that the state space method is a better way of representing systems for the simple reason that it gives us internal descriptions. So now we wonder, like in the last class itself, in the last lecture itself, I had discussed this point that okay, maybe there are no pole zero cancellations within this block G1 and within this block G2, but when you combine them together, it might be that there are pole zero cancellations. So clearly you see there might be a flaw. What is that flaw? If you are given a transfer function like this G1 and G2 in this configuration or in this configuration or in whichever configuration you like, right? What you do is you first in the transfer function domain reduce it to this. So we are still in the transfer function domain here, right? Given a transfer function G1 and G2 connected in any of these configurations, you go from one transfer function representation to this equivalent transfer function representation. And after this, let us say there are some pole 0 cancellations, yeah, and thereafter you go to this SSR, a state space realization. What would have happened by then is that the pole 0 cancellation would have already occurred and you would have missed the critical bit. What is that critical bit? Now if you go to the state space realization and if you check for this lambdas of this A matrix, yeah, those poles which have already been cancelled here, yeah, they will not make their appearance here. So even though you might think, okay, I have these transfer functions, I combine them together, I got the overall transfer function, and then I go to the state space method. So here is the sequence of steps you have done here. So given a transfer function, given multiple transfer functions, I combine to a single transfer function, yeah, and then I go for this state space realization and then I go for this lambda A check, yeah. So what I have is I have multiple transfer functions, I combine to a single transfer function, I am still in the, so basically this part I am doing in the classical domain, I am still in the Laplace transform domain, okay. So this is in the Laplace domain, and then from this Laplace domain I get this state space realization and then I check for the lambdas and I feel okay, I have looked at the lambdas and yeah, those lambdas are all on the left half plane. So then I infer that the overall system is asymptotically stable. This combination of these multiple, after all what are multiple transfer functions? Multiple transfer functions means there are multiple systems, no. So basically this is interconnected systems. So you had interconnected systems, you got their transfer functions. So interconnected systems means each having an ODE, you got to their transfer functions, combine their transfer functions, all this you did within the Laplace domain and then you move to the state space domain. And then you find out this lambda check. You will clearly see the flaw in this method. The flaw is that while you are combining these transfer functions into a single transfer function, it might be that each individual block does not have pole 0 cancellation, but there might be pole 0 cancellation between those different blocks. So for instance, this G1 and G2, they might have common, so G2 might have a pole where G1 has a 0, yeah. Here also you might see that they combine in a certain way such that all the poles of G1 and all the poles of G2, yeah, if you sum together, for example, take this S plus A plus 1 by S plus B. So let me call this alpha, let me call this beta. So you take say alpha S plus alpha B plus beta S plus beta B upon S plus A into S plus B. This is the parallel realization I am talking about, okay. So now you see, if it so happens that alpha plus beta is equal to 1 and alpha B plus beta, sorry, this is alpha B plus beta A, right. So this is S, so this is yeah, A. So alpha B plus beta A is equal to A, yeah. Suppose this condition holds, then what will happen? This will lead to basically a transfer function that looks like 1 by S plus B. So basically the pole that was present in this first transfer function would have already vanished in this realization. Similarly here also you can see that those pole zeros, they might vanish, yeah, there might be some cancellation between G1 and G2, yeah. So not all poles of G1 and not all poles of G2 will make their appearance here in the overall transfer function, okay. So that is why this method is flawed. You might check for this lambda A and you might feel like, okay, if the lambda A's are all on the left half plane, open left half plane, then this overall combination of these systems is asymptotically stable. But you have already reduced them, yeah, you have already reduced them. So what is then the way to do this? The way to do this is this. So this is a wrong method we have seen, right, this is flawed. I hope I have been able to convince you that this is indeed flawed way of checking for asymptotic stability, yeah. So you have, on the other hand, if you adopt this method, you have interconnected systems. From there you obtain the multiple transfer functions like before, yeah, And now instead of remaining within the state space domain, now at this stage itself you realize their state space forms. So at this multiple transfer function stage, when you put them together here, yeah, so for example when you put them together here, instead of going from this route, you get to its SSR1 and SSR2, right. So you go to, from this multiple transfer functions you go to their state space realizations. So multiple systems state space realization, and then from there you combine or merge the SSRs. So what I am saying is, instead of merging at the transfer function stage, get to their state space realizations and then merge them together. Okay. So that way each of these A matrices would have contained all the poles of this system, yeah, and then if you combine them together you will see that the overall A matrix will contain all the poles without the cancellation, and therefore then you check for into a, so you merge them into a single SSR, yeah, and then you check lambda A, yeah. So this is a foolproof way, so this is the way to do. But of course you will immediately notice that there is something that will sort of prevent you from doing this at this stage with the discussions that we have had, which is how to combine these state space realizations into a single state space realization. For transfer functions we know, if they are in cascade we take their product, if they are for example in parallel we take their sum, right. But if we now want to go for this transfer function, I mean this state space realizations, what if two state space realizations are in cascade? Is there a way to see? So what I am saying here is, this is our big question now, yeah. So what I am saying here is, suppose I have a system state space realization given by the 4 matrices A, B, C, D. So you now understand what this means, yeah. I am not going to write x dot is equal to Ax plus Bu, y is equal to Cx plus Du. Basically if I have given you the 4 matrices A, B, C, D, that is how MATLAB also operates. If you want to go from SS to TF or TF to SS, yeah, those two commands, you basically have to enter these A, B, C, D matrices. So any state space realization is of course representable by just giving you the A, B, C, D matrices. So suppose I have this A1, B1, C1, D1 for system 1, which is in cascade with state space realization of the second system A2, B2, C2, D2. And remember we are not trying to avoid, we are now trying to avoid getting from this state space to this G1. So you might think, okay, I do not know how to combine these, but let me go from this state space realization to G1, from this to G2 and then multiply them together. But that isn't going to work, right, that is a flawed method. We have seen that in so multiplying we might actually cancel out some poles and zeros of each of those systems, yeah, among themselves, right. So therefore we now need to figure out a way of merging these together, and it turns out that a little bit of algebra, very small algebraic manipulations will allow us to do this. It is not really very difficult to see how this happens, okay. So let us take an example. I will basically solve it for 3 cases. So those are the 3 basic, and any other block diagram is going to be a combination of those 3 basic cases, alright. So the 3 basic cases, example 1 is this, basically this same thing as I did earlier. So you have this first system, okay, let me write here x1 dot is equal to A1 x1 plus B1 u, and y1 is equal to C1 x1 plus D1 u. So this is my u. But what is the output here? The output here is y, and this is the crucial bit. Once you have observed this, the output here is y1, I am sorry, and this is the crucial bit. So now when I am writing the equation of the second system, the states of the second system are, so this is system 1 and this is system 2. So when I am writing this x2 dot, I will write A2 x2 plus B2 times, now what is the input here? It is no longer U, you see. So it is going to be Y1, right, and Y2, yeah, is going to be nothing but C2X2 plus D2 Y1, and what I have then is Y2, and I know that from this interconnection Y2 is equal to Y. So basically I need to find the relation between this U and this Y, which is basically this U and this Y2, and I have to eliminate all the other intermediate terms like this Y1, yeah, that is what I need to do. So let me write that down a little more formally. I am going to be more interested in this second case, yeah. So of course if I write x2 dot is equal to a2 x2 plus b2, and I am going to substitute this expression for y1 here, b2 times c1 x1 plus d1 u, alright, which is going to be a2 x2 plus b2 c1 x1 plus b2 d1 u, yeah, and y2, which is indeed nothing but y, that is going to be c2 x2 plus d2 times, again I am going to just substitute this y1, which is nothing but c1 x1 plus d1 u. Therefore I am going to come up with c2 x2 plus d2 c1 x1 plus d2 d1 u. So note, I am going to now focus on this y, and that is equal to this. So this is my overall output equation, yeah, this blue part is my overall output equation, this y being equal to this. What is my state equation? Notice that for the state equation of x1 dot is going to be nothing but a1 x1, yeah, plus 0 x2 plus of course b1 u, and x2 dot is going to be, this is going to be interesting, x2 dot is going to be b2 c1 x1. So although these are vectors, these x1 and x2, you can see the analogy between this vector representation and the way we write simultaneous equations, right, like scalars. So b2 c1 x1 plus a2 x2 plus what I have here is b2 d1 u, b2 d1 u. So compact form, if I combine these, concatenate these two vectors, so let us say this is of size n1, so this belongs to R n1 and this belongs to size R n2. So I now write this as a combined vector which belongs to size R n1 plus n2, yeah. What is that going to be? Here is what it is going to look like. So it is going to look like a1 b2 c1 a2 0 plus b1 b2 d1 times u, and of course the y matrix I can write now. Notice, so this is my overall C, so my y matrix is now going to be, y is going to be C is what times x1, d2 c1 times x1, so it is d2 c1 times x1 and c2 times x2. Sorry about that, I have really made a bad error here. I should write x1 x2 plus this, yeah, x1 x2 plus what is this here? It is d2 d1 u, d2 d1 u. So now my overall system matrix is this A, overall B matrix is this B, overall C matrix is this C, and overall D matrix is this D, yeah, just small algebraic manipulation here, and I have got the overall state space representation of two systems that are put in cascade, yeah. So if I know the state space realization of two individual systems in cascade, then I know the overall state space realization of the combined system. Yeah, this is the way to do it. Just like we had that multiplication may not be as simple as multiplication, but once you practice a bit of this and grow familiar with this form you will be able to see immediately, right. It might even be worth committing this to memory. I am not suggesting you do that, but even if you do not commit this to memory, you can just derive, in a minute or so you can derive this combination of these two, right. So this is going to be your overall merged combined system, and now in order to check for asymptotic stability, all that you need to now focus on is look at lambda A, that is it. And notice how very interesting this is a triangular block triangular matrix. So again a bit of linear algebra will tell you that the eigenvalues of this A matrix are nothing but combination or the union of the eigenvalues of A1 and those of A2, which is to say, if I now go back to this transfer function representation, yeah, if I go back to this transfer function representation, it means that instead of merging these transfer functions together like I did here, if I had just taken the poles of this one alone and the poles of this one alone, right, and then I had looked at whether all of those poles are in the left half plane, I would have inferred the same thing about asymptotic stability, right. So if each of those individual systems is asymptotically stable, then the overall system is also going to be asymptotically stable, right. Of course, assuming that there is no pole zero cancellation within an individual system, it does not make sense to have a system where there is a pole zero cancellation within itself. After all, it is a hardwired system, no, as I said, yeah. So that is the notion of this combination. Just to give you another idea about how this merger happens, I will take the parallel case as well. So this is basically x1 dot is equal to a1 x1 plus b1 u, y1 is equal to c1 x1 plus d1 u. So this is my u, so this is my y1, and similarly if I now come to this case here, I will have x2 dot is equal to a2 x2 plus b2u. Note that both of them have the same input here now, yeah, unlike in the earlier case where the output of the first system became the input of the second, here both of them have the same input u, and this y2 is going to be equal to c2 x2 plus d2u, and then they get added. So this becomes your overall y. So how am I going to write this? This is actually pretty straightforward here. The only thing that happens here is the y gets changed, everything else remains the same. So I can just write this as x1 dot is equal to a1 x1 plus 0 times x2, yeah, plus b1 u, and x2 dot is equal to 0 times x1 plus a2 times x2 plus b2 times u, right. And what about y is equal to y1 plus y2, so that is going to be nothing but c1 x1 plus c2 x2 plus d1 plus d2 times u. So if I now write this in the compact form, notice as before I am going to concatenate these vectors together and I am going to write this in the compact form. So look once again, this time it is going to be even simpler, it is going to be a block diagonal form, right, yeah. So you have this x1 x2 sitting here plus yeah. So notice here what did we have here? Here we had a block triangular form, right. So in the case of the block triangular form, all right, if you notice that what was the situation going to be here like? We said that we want to infer about the eigenvalues of this, so you better infer about the eigenvalues of this overall matrix. Here also by the same token, this is the A matrix that we will be interested in for our eigenvalues, and here it is very transparent, it is just those of A1 and those of A2, that is all that the eigenvalues of this overall A matrix can be like, and this is going to be B1, B2, yeah, times u, and your y is going to be C1, C2 x1 x2 plus d1 plus d2 times u. So this then becomes the overall B matrix, this becomes the overall C matrix, and this becomes the overall D matrix. Yeah. So we have seen at least two kinds of the cascade combination of two state space realizations. We have seen what the equivalent state space representation is. Now we have combined the parallel combination of two state space realizations, and we have seen how this is. Next, what we are going to look at, and this does not always stand up to scrutiny, because remember, a state space realization can only be obtained for systems which have, the crucial important thing is, a transfer function that is at best biproper, right. Either it is going to be strictly proper or biproper, right. If it is not, if it is improper, of course there are some polynomial matrix descriptions. So again, that's very sophisticated concept, so I am not going to go into that. So you sometimes do represent systems, yeah, as some JS like this. Yeah, we will not deal with those systems in our course. In fact, even in many sophisticated courses, this is clearly bypassed. Sorry, this is not D, this is C. Yeah. So in that case, you might be able to accommodate some of these things, but we consider this last bit to be constant D. So with this constant D, the most we can get to is biproper transfer functions. Yeah, we cannot get to improper transfer functions, right. So then it means that if GS and G inverse S are both state space realizable, what can we say? If GS is state space realizable, then the degree of the denominator of GS better be greater than or equal to the degree of the numerator of GS. But if G inverse S is also state space realizable, yeah, then the degree of the numerator better be greater than or equal to the degree of the denominator of GS. Yeah. So combining these two together, the only situation when we can have both G and G inverse state space realizable is when D is not equal to 0. We are talking about CISO, of course. For multi input multi output, you know, D has to be non-singular. Yeah, but the CISO case equivalent is that D is not equal to 0, because if D is 0, then GS is strictly proper. If GS is strictly proper, then G inverse is going to be strictly improper. So G inverse cannot be realized by state space, right. So therefore, the third exercise is, for a given SSR, say A, B, C, D, we want to obtain the representation of the inverse system. So if we want to obtain the representation of the inverse system, it better exist first, right. If it has to exist, then the condition is, the assumption is that D is not equal to 0, because otherwise this question makes no sense. Okay. So why is this important? Because often you will encounter this 1 plus GS appears in the denominator, right. What is 1 plus GS? If you look at 1 plus GS, this 1 is like a constant, right. So 1 plus GS is always going to be biproper, right. 1 plus GS is always going to be biproper. So therefore we often have this sort of thing where G by 1 plus GS we want to realize, right. So that is like saying that we have a G block here and sort of a 1 by 1 plus G block here. Yeah. So suppose we have a state space realization for 1 plus G, of course. So can we get a state space realization for 1 by 1 plus G? Yeah. So 1 plus G is state space realizable. So can we get a state space realization of 1 by 1 plus G? Yeah, that is the question. If we can, then we can then apply the cascade rule and get the state space realization of this, state space realization of this, and merge them in cascade like we did here. So it's a combination of two steps. First step, get the state space realization of the inverse, then get the state space realization of the cascade. Okay. So for that purpose this may be necessary, but now we have seen that for the inverse to exist, this D must needs necessarily be non-zero, as will be the case for this. If you try to realize this state space system, the D will always be non-zero because it is going to be biproper. So it makes sense then. So that is a standing assumption that we are not making just for the sake of it, but it is because that for the inverse to exist, that D must be non-singular, in our case non-zero. So enough said, let us see how this representation is. So the original system is x dot is equal to Ax plus Bu, y is equal to Cx plus Du. So this is the original system, in which the input is applied from this side and the output is taken out from this side, alright. Now you might ask, so what is the depiction of this inverse system in this block diagram, like when do we say that this is indeed an inverse? Well, it turns out that the inverse notion of this inverse is likewise, if instead at the output terminal you had given an input, yeah, so if you had just flipped the direction of the arrow and at the input terminal you had given the output, or rather maybe I should not flip it like this, what we are saying is that if you give an input, at the input terminal you applied this output, at the output terminal you would get back this input. So it is like the inverse mapping, yeah, that is what the inverse system is. So this is going to be then some x tilde dot is equal to A tilde x tilde plus B tilde u, sorry, actually you do not need to name this x tilde because after all the states of the system are still going to be the same, right. So here now this input is going to be y and the output signal is now u. So that is going to be this, in fact this is just, it is the excitation, no? So we do not need the B tilde, we will name the B tilde later, sorry about that confusion. So you just have to just see that at the input now you have the y signal, so it is just Ax plus By, and at the output you have u, so that is going to be Cx plus Dy, right. So this is how our system's description is, right. Now we want to get the state space realization from u to y, remember this is because we have now applied this inverse thing and we have got this. So we applied the output at the input terminal and we got the input at the output terminal, that is what we are now considering here, right, but that is what the inverse system does. So now we wonder what the overall state space representation is going to look like. You see this y, yeah, when you now put this in combination with this, how do I put it here, yeah, so this is your ut, right. So now if you had put this in combination with the original system, that is x dot is equal to Ax plus Bu and y is equal to Cx plus Du, then this would have resulted in the identity mapping, no, just like you had G and G inverse and you get back the same signal, right. So here if you gave the output here, you got the output back here, you gave y here, you got y here. Similarly if you had combined this inverse system here, so before doing the algebra I just want to make that notion very clear what this inverse means. So this is x dot is equal to Ax plus By, u is equal to Cx plus Dy, yeah, so you get back this u, yeah, so that is what the crux of the matter is. So now point is, how do we get this overall representation done, okay. So here is what we are going to do. So you see, if you plug in this u here, what are you going to get? X dot is equal to Ax plus By and u is equal to Cx plus Dy. So from this you get, because D is non-zero, we can divide throughout by d. So I am going to write d inverse to be a little more generic, but we will say that d inverse exists, but for the seesaw case you know that it is just 1 by d. So then y is going to be d inverse u minus d inverse cx, yeah. And now if I plug in this y here, sorry, this expression for y here, if I plug in this expression for this y here, I wonder what I will get. So what I will get is this x dot is going to be equal to, as before, ax plus b times, and now I am going to substitute for this y, so that is d inverse u minus d inverse cx, d inverse u minus d inverse cx. So that is going to be a minus b d inverse c times x plus b d inverse u, and y, we have already gotten its expression in terms of u, is going to be minus d inverse cx plus d inverse u. So if you want to write this in the state space form, what is its representation? You see, this is now going to be my A matrix, this is going to be my B matrix, this with the minus sign is going to be my, okay, let me call this A bar, B bar, this is going to be my C bar matrix, and this D inverse is going to be my D bar matrix, right? That is all there is to it. So basically we have seen that if you have three different types of combinations of state space realizations, first you put them in cascade, we have seen how to get the overall state space realization in cascade, then you put them in series, in parallel, and we have seen how to get that, and now we are saying that, well, if you take the inverse, yeah, if you take the inverse of that transfer function, then here is what you get. Yeah, then you better look at this particular A matrix. So now if you want to check for the asymptotic stability of the inverse, then well, the eigenvalues of this A bar or the eigenvalues of A minus B D inverse C, these better be on the open left half plane. Yeah, if these are not all on the open left half plane, then the inverse will exist, but the inverse will not be asymptotically stable, right. So these are the reasons why we went into this. So let me quickly recapitulate why we went into this state space combination of systems, because we saw that, well, just give me a second here, yeah, because we saw that there was something severely flawed with this method of checking for stability. That is, if we go via the Bibo stability route, which is to say that if we merge the transfer functions together in the Laplace domain itself and then get it to its state space realization and then check for the eigenvalues, we might have already cancelled out some poles and zeros inadvertently while merging the transfer functions together. So therefore, a better idea is you have different systems, take their state space realizations already before merging them together, and then merge them as different merger of state space realizations, a merger of different state space realizations rather than merger of different transfer functions. Yeah, that way you will be able to preserve the structure of the A matrix, and thereafter if you just look for the eigenvalues of the overall A matrix, that will tell you about the asymptotic stability, okay. Yeah, so that is basically the crux of this discussion, okay. So I hope that with that we have kind of nicely wrapped up on whatever we wanted to discuss. There is, of course, there is no limit to the depth to which one can go in pursuit of these ideas of stability and things like that, but we will have to put an end to it here at this juncture. If you want to go further along these directions, there are courses such as those on robust control, which talk about these state space realizations and also how to design controllers. In our course also we will see a very rudimentary kind of a controller design technique, a state space pole placement or a state feedback kind of a controller design, but that will be probably the last, one of the last topics we will discuss. We will see the design of a controller and the design of an observer, and that will wrap up our course. But of course, these state space realizations that we have just shown you how to merge them together in the state space domain, these are very useful and particularly useful when after a point when you design controllers, So you basically have something like a plant whose SSR is given, yeah, and you are allowed to design a controller. So this is basically the plant, this is the controller. So the SSR of the state space realization of the controller is also given, yeah, and instead of now placing the designing the poles and zeros of the transfer function like we did using some root locus based technique or Nyquist or whatever design technique you might have, now you want to basically directly say that what the state space realization of the controller is that meets your performance metrics or that meets your performance goals, right. So we design controllers directly in the state space domain, okay. So that is regularly and routinely done in courses or in topics such as robust control, right. So therefore it is very important in such courses or in such domains to be very familiar with, just like you are now very familiar with how to merge transfer functions together, whether they are in cascade or in parallel or in a feedback configuration. So also should you try and familiarize yourself with how these different state space realizations, when they are put in cascade, when they are put in parallel, when they are put in feedback configurations, how they can be merged together and written in a compact matrix form, okay. So hopefully this brief discussion we have had in this lecture will be a stepping stone in that direction, and you might practice a few problems and see that indeed this agrees with whatever we know about overall transfer function to state space realizations, yeah, going from transfer function to state space and state space to transfer function. Take some examples of transfer functions, merge them together in the transfer function domain and then realize it in the state space domain, and then do the reverse, that is take the transfer functions, go to their transfer function state space realizations and merge them in the state space domains, yeah, and you see that you will end up with the same thing provided there are no pole zero cancellations between these individual blocks. So having seen the state space realizations for those three types of interconnections, that is the cascade, the parallel and the inverse of a system, I leave this as an exercise to you to write down the state space realization for an interconnection which is in a feedback loop, whether it is positive or negative, but if it is in a feedback loop then get the state space realization for G and that for C, and then find out what is the overall state space realization of the system and then derive what should be the condition for the stability. You will see that the A matrix will be rather more complicated than the cases that we have handled so far, right. Okay. So next topic that we are going to see, I am just going to briefly introduce in this lecture and we are going to see much more details of this. So the next topic is going to be this notions like things that have been pretty mystifying up until this point because I have just loosely mentioned them in passing often: observability and controllability, okay. So I shall just provide you with some motivation for studying these problems in this lecture today. There will be some early motivation for this, right, and then we shall get into the rigorous technical nitty-gritties and details in the upcoming lectures. So what is this notion of observability? At the very rudimentary form, let me take you back to how we started our discussions on state space systems. So what did we do initially? We put this bank of these integrators, if you recall, right. We had these bank of integrators for a state space realization, right. Even before that we had this third order differential equation, third degree differential equation. I don't remember in which order I put the coefficients, maybe I don't recall exactly. So this was what it was, something like this, no, minus a1 y double dot minus a0 y plus b2 u double dot plus b1 u dot plus b0 u. Yeah, this was how we wrote it, and then we integrated this thrice. Yeah, recall. So this is just a reprisal of what we've already done. So this is going to be like, y is equal to minus a2 times integration of y minus a3 times, sorry, this was I unnecessarily put two dots here, excuse me, this will just be one dot. So this is twice the integration of this, and minus a0 times thrice the integration of y, yeah, and then we had this plus b2 times the integration of u plus b1 times twice the integration of u plus b0 times u. Yeah, and this we realized, we saw that with this we put these summers here, so excuse the bad drawing here, but that is because I have already explained what this means earlier. So this we called y, then this one we passed through once only, so this was minus a2. Yeah, so minus a2 times y integrated once, then minus a3 times, oh sorry, a1 this was, right. So this is minus a1 times integrated twice, yeah, very bad drawing I am afraid, and then we had a summer here too, so this was minus a0 times, yeah, I am being very casual about this because we have already seen this picture already, right. And what else did we have? We of course we also had to integrate this u here. So one time we had this b0, this u passing here, and then we had to take this b0 and integrate it twice. So we put in this had to be integrated twice, so we put in this, sorry, what was that, b1. So this was b1, we put it like this, yeah, and then we had this other time that it had to go through once, that was b2, yeah. So this is how we realize this. Remember, a very bad drawing, I apologize for this bad drawing, but I am just doing this in a loose fashion because we have already drawn this elaborately many classes back. It turns out that this particular form of realization has a name which I withheld up until now, or maybe I mentioned in passing, I do not recall. So this is called the observer canonical form, okay. And now when we understand this notion of observability, this will be actually a little clearer to us. So when we realize things using these op amps which act as integrators, yeah, think of the problem in this fashion. We have been given this analog computer, alright. So this entire thing here is within a black box. We have no access to this, suppose. In practice you would see that all these integrators are accessible and you can actually feed in voltages to these integrators, right. But suppose this is a complete black box, it is like the analog computer comes out in a comes in a boxed package. You just have a wire that goes in and a wire that comes out, an input port and an output port, and whatever is inside you know it is this, but you are still not very sure that you can use this in a handy way. Why is that? Because you want to use this analog computer to simulate or solve for this differential equation given certain initial conditions. Now suppose I give you a particular initial condition. How many initial conditions do you need? So suppose I give you some y0, y dot 0 and y double dot 0, yeah. Suppose I give this to you, say some typical value 1, 3, 5, 1, 3 minus 5, whatever it is. So given that this whole thing is inside a black box, yeah, how are you on earth going to determine what should be the input, the initial condition of this integrator, the initial condition of this integrator and the initial condition of this integrator? Pay very careful attention to this question. What is my question? My question is as follows. I am required to solve for a differential equation using this analog computer. I do not have individual access to these integrators, okay. So I cannot put a multimeter, yeah, next to this integrator and just figure out what its initial condition is, yeah. So that's the first thing, and neither can I rip it open and apply any initial value to it. So neither can I just apply a voltage source and feed this integrator through a voltage source to set its initial value to a certain level, alright. So there are two problems here. What is the first problem? And this will form the crux of our understanding of observability and controllability. Let me get a little ahead of myself and say this. Many students we found that over the years when we ask about observability and controllability, instead of discussing what observability and controllability means, Yeah, we will give two interpretations here, but what most students they do is they give us the condition or a test for observability and controllability. So it's like, you know, we have been discussing this asymptotic stability notion. If I ask you what is this definition of asymptotic stability, and you tell me that the eigenvalues are of the system matrix A are all on the left half plane, you won't get any credit for that. That's a way of checking for asymptotic stability. It's an equivalent condition for asymptotic stability. But at the heart of asymptotic stability is this fact that as t tends to infinity, the vector xt, its norm, that is each and every component of that vector must go to 0. That is the definition of asymptotic stability. Yeah. So similarly for Bibo stability, if I ask you the definition of Bibo stability and you tell me the poles of the transfer function must be all on the open left half plane. No, that's a check, that's a way of checking whether a system is Bibo stable. If you want the definition, then it should be, if I give you a bounded input as an input to a system, the output should also be bounded. Or a more sophisticated technical definition is the impulse response of the system, yeah, should be absolutely integrable. That is the definition of Bibo stability. Okay. So by the same token, when we ask about observability and controllability, it is important to understand what observability and controllability mean, rather than just to, you know, spit out some conditions like the rank condition on certain specially cooked up matrices. It gives no insight. That's a handy way of testing. So here's what we are trying to explain. So if you understand this problem, you will at least get one flavor or one feel for what observability and controllability entail. So now, this is the differential equation, this is the analog computer that allows you to solve for this particular differential equation given any initial condition. Now, I give you this initial condition that y0 is equal to 1, y dot 0 is equal to 3, y double dot 0 is equal to minus 5, and I ask you to solve for this. Now you are in a quandary, right? You first think there are two things that are hurdles to your way. The first hurdle is, right, y0 is equal to 1, y dot is equal to 3, and y double dot is equal to minus 5 at this instant initial condition, right? But what should be the initial conditions of these integrators? Because note that these integrators, are they going to directly be this y dot and y double dot? Yeah. So if this is y, then this is y dot. So in this form, it turns out that gives us some convenient notion, but if it's any arbitrary realization, from y can I get this? So remember, the problem is as follows: I am given initial conditions in terms of y0, y dot 0, dot 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 till some rth derivative of y, I do not know, some n minus 1th derivative actually. Yeah, for nth degree differential equation you need you need the initial condition of y and it up to its n minus 1th derivative. That is the typical initial value problem, right? You need n initial conditions to solve it. Yeah, so I have been given this. So I am given initial conditions in terms of this. Can I determine, so this initial condition is 0 minus, maybe 0 minus, 0 minus. Can I determine what x1 0 minus, x2 0 minus, dot 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 till xn 0 minus should be for these initial conditions? Yeah. So remember, I have numerical values for this. So this may be 1, this may be 3, this may be minus 5, as I have chosen in the previous slide, right? But I still do not know what x1's initial condition, x2's initial condition and xn's initial condition is. It turns out that for certain forms of realization such as this, it may be easy to obtain. But what about some other form of realization? As we have seen, there are different state space realizations, right? So the question is that given any state space realization, yeah, I do not know how that analog computer is connected inside, I do not know about the wiring, I just know that it solves this particular differential equation. That is how someone has connected it and given it to me. And now I am told that this is the initial condition in terms of y, and you better feed this x such initial condition so that these y's are set up for this solution. So remember, when you are solving, these days you use MATLAB, when you are solving a differential equation using Runge-Kutta or any other method, what you generally do is you feed in some initial condition as an initial condition to the ODE, and then you propagate that initial condition through the dynamics of the system. So here also you have to propagate this initial condition, but for that you need to know what the initial condition at each of those integrators is going to be. This is the problem of observability. Given the initial condition in terms of the output, can I translate it to, or can I obtain the initial condition in terms of the states? Because if I can, then I have some hope that I can fit in those initial conditions to my integrators, because as we have defined that the output of each integrator is a state in this rudimentary definition. So if we can do that, then we can set it up. The second question, can we set it up? I just said we can set it up. What do I mean by can we set it up? Remember, we are assuming that this is all inside a briefcase, maybe this analog computer, or inside a big box. So the only access I have to it is at the input channel is through this U. So now my question is, okay, I have found out that you give me this, you've given me this y0 is equal to 1, y dot 0 is equal to minus y dot 0 is equal to 3, and y double dot 0 is equal to minus 5. And for that I have, let's say I have found that I need, for my particular realization, x1 0, x2 0. So based on the wiring diagram that's drawn on the top of the briefcase, yeah, I have done some computations, never mind how I have done those. I have figured that this should be 2, 4 and minus 7. Yeah, so this matches. So if I set my initial conditions of the integrators to 2, 4 and minus 7, then the initial conditions at the output y double dot and y dot, they turn out to be 1, minus 5 and 3. Now the point is, if this is what I have to set at the input, at the initial condition of each integrator, how can I set it? The only way to set it is by giving some input voltage to this U. But is it guaranteed? Yeah, is it guaranteed that I can always cook up some U which will give me exactly the initial conditions, which will allow me to set the initial conditions of each of these integrators to this 2, 4 and minus 7? That is the problem of controllability. Okay, so can I take through this access that I have to the system through this input channel? Yeah, so here's the catch. Through the connection that I have, or access that I have to the system through the input channel, can I pass an input which will allow me to set any arbitrary initial condition of those integrators? Yeah, can I, in other words, can those states assume any possible value through my input channel? Can I make the states go to any possible value through the input channel? So given an initial condition of the states, I want to push it to any other condition which suits my initial conditions for the differential equation. Can I drive a state from any value to any other using this input? That is controllability. Observability, reading off the output from the output terminal. The only access I have for the output is the output terminal. I cannot connect multimeters to the output of the integrator separately. Yeah, so reading off this output at the output terminal, can I determine what the corresponding state values are? Yeah, that is the problem of state observability, whether the states can be observed based on the information I have of the output, that is observability. Whether the states can be driven from any value to any other value, given that I am allowed to apply some input at the input channel, that is the controllability problem. Okay, that is the motivation. Now you might think, so I'll end this. So this is basically the motivation and the way to define observability and controllability. You might think, well, you can just open the box. I mean, this is after all an analog computer, which is why this problem is not very meaningful for the analog computer, you might say, and then why study controllability and observability? But now think of a system that is very remote and you don't have access. It's not a simulation block, okay, it's not a simulating system. Yeah, so think of this system where you don't have access to all these different states, yeah, or neither can you read off all these states from the output. What do you do then? Right, that is the problem, right? So then systems are said to lack in observability or controllability, and it's a serious issue. Okay, so that's why we need to understand when a system is observable and when a system is controllable. We'll get more into the details and the mathematical nitty-gritties of this in the next lecture, but hopefully in this lecture you've at least been introduced to these ideas of what observability and controllability entail.